In this contribution, we present a novel approach for the physically accurate simulation of clouds based on first principle formulations for computing buoyancy and air pressure that account for variations of atmospheric density and temperature gradients. We introduce the amount of heat emission and its variation, as well as the relative humidity on the ground and its variation as lightweight means for simulating different cloud formations, while maintaining interactive rates for rendering. Moreover, ground noise parameters can be adjusted to allow variations of the underground. Starting from an empty scene, fog can easily be generated by emitting heat from the ground while maintaining a high humidity. To transition the fog into stratus, heat emission has to be slightly increased and humidity decreased. Stratocumulus can then be generated by increasing the variations of heat emission and humidity. Noise should be enabled and appropriately adjusted depending on the desired cloud patterns. To further transition to cumulus clouds, heat emission should be increased and humidity further decreased. Variations of heat emission and relative humidity should be increased and noise slightly reduced compared to the stratocumulus setup. By increasing the variation of heat emission, cumulus clouds can then be further transitioned into the cumulonimbus shape. Here, we show a visualization of smooth cloud transitions from fog over stratocumulus to cumulus from left to right. Between the corresponding cloud type parameters, linear interpolations are carried out. The characteristic high fog around Half Dome in the Yosemite National Park is simulated here. In this scene, a sea breeze moves clouds built up over the Atlantic Ocean to the Irish coast, rising up the mountains. In contrast, in this scene, a land breeze moves the clouds away from the coast. Here, we see the development of heavy rain over the Alps caused by a cumulonimbus cloud. We are able to simulate the temporal evolution of different types of cloud supercells. To further showcase the capabilities of a physically accurate cloud simulation model, we coupled our framework with atmospheric measurements of online weather services to simulate cloud formation in real time, enabling weather nowcasting. Thank you for your interest in our work and watching this video.